Exercise 6.12. The plane pi is given by the equation r is equal to 2i plus 7j plus 3k plus lambda times 7i plus j plus 3k plus mu times 3i plus 2j minus 5k. The point T has position vector 7i minus 13j minus 2k. Find the distance between the point T and the plane pi. Let me write this in a form that I prefer. So pi has vector equation r of lambda and mu equals 273 plus lambda times 713 plus mu times 32 negative 5. And we also have the position vector of the point T is 7, negative 13, negative 2. Alright, now we're in business. It says find the distance between the point T and the plane pi. So first I guess we would like a normal vector of our plane pi. So let's take the cross product of 713 and 32 negative 5. Since those are the direction vectors of the plane. 3, 2, negative 5. Okay, so 1 times negative 5 is negative 5, minus 2 times 3, so that'll be negative 11. And then 3 times 3 is 9, minus negative 35, so that would be positive 44. And then lastly, 7 times 2 is 14, minus 3 is positive 11. And we don't have to take that particular normal vector if we don't want to. We can also take the normal vector n1 is this thing divided by 11. So it'll be negative 1, 4, and 1, just to make life a bit easier. So that means the equation of pi in Cartesian form is negative x plus 4y plus z is equal to d for some number d. And of course we know that r of 0, 0, which is just equal to 273, is in the plane. And so substituting these coordinates into the x, y, and z coordinates should make the equation true. So that means we have negative 2 plus 4 times 7, which is 28, plus 3 is equal to d. And so that would tell us that d is equal to 29. So actually the equation of the plane pi is negative x plus 4y plus z is equal to 29. Not only that, but we're looking for the distance between the point T and the plane pi. And if we draw ourselves a little sketch of what's going on, we have our plane pi here. Okay, and we have our point T up here, which has coordinates 7, negative 13, negative 2. And we have our normal vector n1, negative 1, 4, 1. Then if we put our origin over here, we know that OT plus some multiple k times n1 is going to land us in the plane. Because OT, well, k times n1 is this vector here. This is the vector k times n1. The way I've drawn it, you would expect k to be negative, but I don't actually know what direction n1 is pointing in, so don't be surprised if it's positive. And so that will arrive us at some point f for the foot of the perpendicular. So that's equal OF Alright, so writing that in full, we have OT is 7, negative 13, negative 2, plus k times n1, so that will be minus k plus 4k plus k. Alright, and that is supposed to be inside our plane, which means the x, y, and z coordinates of this should satisfy this equation here. So we have that negative of 7 minus k, so that will be k minus 7 plus 4 times 4k minus 13 plus z, so that would just be plus k minus 2. That's equal to 29. So we have, well, k minus 7 plus 16k minus 52 plus k minus 2 equals 29. And then, I guess, 18k in total on this side. And then let's move everything to the other side. So 29 plus 2 makes 31, plus 52, that would be 83, plus 7 makes 90. And so I guess that means that k is equal to positive 5. And then from there, observe that the distance between the point t and the plane pi is simply the length of this vector k times n1, where k is equal to 5. So therefore, distance between t and pi is equal to the length of k times n1, which is equal to the length of the vector 5 times, and n1 was negative 1, 4, 1. So that's equal to 5 times the square root of 1 plus 16 plus 1. So that is equal to 5 times the square root of 18. Or you can also write that as 15 times square root of 2, if you prefer. And that's all for this question.